Hey there, science enthusiasts! Today, we're diving into the fascinating world of inverse functions. These mathematical marvels have the power to reverse actions like rewinding a movie. Just like subtraction undoes addition, inverse functions have the unique ability to undo the effects of their counterparts. Intrigued? Let's embark on this exciting journey to demystify inverse functions and explore their significance in the realm of mathematics. Buckle up, because we're about to unlock a whole new level of mathematical understanding. A closer look. Imagine a function as a special machine that takes an input, processes it, and produces a unique output. Now picture an inverse function as another machine designed to reverse this process, taking the output from the original function and transforming it back into the original input. Pretty neat, right? But here's the catch. Not all functions have inverses. For a function to have an inverse, it needs to be a one-to-one function, meaning that each input maps to a unique output and vice versa. In simpler terms, no two different inputs can have the same output. Think of it like a secret code where each letter has only one corresponding symbol. Ready to roll up your sleeves and find some inverses? Here's a handy step-by-step guide to help you crack the code. First, replace fx with y. Let's start by swapping out that fancy efx with a simple y. It's like giving our function a temporary nickname. Next, swap x and y. Now let's switch the positions of x and y in our equation. It's like playing a game of musical chairs with variables. Then, solve for y. Our goal is to isolate y on one side of the equation, making it the star of the show. Finally, replace y with f circumflex 1 x. Time to bring back the inverse notation. We replace that isolated y with f circumflex 1 x, signifying that we've successfully found the inverse function. Let's put our newfound knowledge into practice with a real-life example. This will help us understand the concept better and see how it applies in real-world scenarios. Suppose we have the function fx equals 2x plus 3. This is a simple linear function, and our goal is to find its inverse. Our mission to find its inverse. Ready, set, go. Let's dive into the steps and see how we can achieve this. First, replace fx with y. This substitution makes it easier to manipulate the equation. We start by writing our function as y equals 2x plus 3. This is our starting point. Next, swap x and y. This step is crucial as it sets the stage for finding the inverse. Time for a variable swap. This means our equation now looks different. Our equation now becomes x equals 2y plus 3. Then, solve for y. This involves isolating y on one side of the equation. Now let's isolate y by subtracting 3 from both sides and then dividing both sides by 2. This will give us the value of y in terms of x. This gives us y equals x minus 3 divided by 2. We are almost there. Finally, replace y with f circumflex 1 x. This notation indicates that we have found the inverse function. We replace y with f circumflex 1 x, giving us the inverse function f circumflex 1 x equals x minus 3 divided by 2. Ta-da! We've done it. We've successfully unmasked the inverse of our linear function. Great job, everyone. Now you can apply this method to other linear functions. Section 5. Example 2. Deciphering the inverse of a rational function. In this section, we will delve into the intriguing world of rational functions and their inverses. Let's tackle a slightly more challenging example involving a rational function. This will help us understand the process in a more comprehensive manner. Consider the function f of x equals x plus 1 over x minus 2. This is a classic example of a rational function. Can we find its inverse? Absolutely. With a systematic approach, we can unravel this. First, replace f of x with y. This substitution is crucial for the next steps. We begin by rewriting our function as y equals x plus 1 over x minus 2. This sets the stage for finding the inverse. Next, swap x and y. This is a fundamental step in finding the inverse. Now it's time to swap those variables, giving us x equals y plus 1 over y minus 2. This new equation is the key to our solution. This step requires a bit of algebraic manipulation. We need to carefully handle the terms to isolate y. We multiply both sides by y minus 2, distribute, and then rearrange the terms to isolate y. This process involves several steps, so take your time. After simplifying, we get y equals 2x plus 1 over x minus 1. This is our simplified inverse function. Finally, we replace y with f inverse of x, revealing the inverse function f inverse of x equals 2x plus 1 over x minus 1. We've done it again. This final step confirms our solution. We've successfully deciphered the inverse of our rational function. Congratulations on mastering this challenging concept. Section 6. Graphing inverse functions. A reflection of symmetry. Graphing inverse functions is like discovering hidden patterns in a mirror. The graphs of a function and its inverse have a special relationship. They are reflections of each other across the line y equals x. Imagine folding the graph paper along the line y equals x. The function and its inverse would perfectly overlap. This reflection makes sense because inverse functions swap the roles of x and y. So, if a point, AB, lies on the graph of the original function, then the point, BA, will lie on the graph of its inverse. It's like they're trading places in a perfectly choreographed dance. Section 7. Practice makes perfect. Test your inverse function prowess. Ready to put your inverse function skills to the test? Here are a few practice problems to challenge yourself. 1. Find the inverse of the function f of x equals 3x minus 5. 2. Determine if the functions g of x equals x plus 4 divided by 2, and h of x equals 2x minus 4 are inverses of each other. 3. Given the function f of x equals the square root of x plus 9, find its inverse function, f inverse of x. Remember to use the step-by-step guide we learned earlier, and don't be afraid to experiment. The more you practice, the more confident you'll become in finding and understanding inverse functions. Section 8. FAQs. Addressing common queries about inverse functions. In this section, we will delve into some of the most common questions students have about inverse functions, providing clear and concise answers to help you understand this important mathematical concept. Let's address some frequently asked questions about inverse functions, which are crucial for understanding higher-level mathematics and various applications in real-world scenarios. Q. What is the significance of the notation f inverse of x? This is a common question that often confuses students. A. The notation f inverse of x represents the inverse function of f of x. It essentially means that if you apply f to x, and then apply the inverse function, you will get back to the original value of x. It's important to note that it doesn't mean 1 over f of x. This is a common misconception that needs to be clarified. Q. Can all functions have inverses? This is another frequent query that students often have. A. No. Not all functions have inverses. Only certain types of functions meet the criteria for having an inverse. Only functions that are one-to-one, meaning that each input has a unique output, can have inverses. This ensures that the function can be reversed without ambiguity. Q. How can I verify if two functions are inverses of each other? This is a practical question that often arises during problem solving. A. You can verify if two functions, f of x and g of x, are inverses of each other by checking if f of g of x equals x and g of f of x equals x. This double check ensures accuracy. If both of these equations hold true, then f of x and g of x are indeed inverse functions. Understanding this verification process is key to mastering the concept of inverse functions. Section 9. Conclusion. The significance of inverse functions in mathematics. Inverse functions play a vital role in various branches of mathematics and beyond. They allow us to solve equations, model real-world phenomena, and unlock a deeper understanding of mathematical relationships. By reversing the effects of functions, inverse functions provide us with a powerful tool to analyze and manipulate mathematical expressions. From solving for unknown variables to understanding the behavior of complex systems, inverse functions are essential tools in the toolkit of any math enthusiast. So, embrace the power of inverse functions and continue to explore their fascinating properties. Section 10. Bonus section exploring real-world applications of inverse functions. Inverse functions aren't just confined to textbooks, they have real-world applications in various fields. Cryptography inverse functions are used to encrypt and decrypt messages, ensuring secure communication. Computer science. In computer graphics, inverse functions are used to create realistic images and animations. Physics, inverse functions are employed to model physical phenomena, such as the relationship between distance, velocity, and time. These are just a few examples of how inverse functions are used to solve real-world problems. As you delve deeper into different disciplines, you'll likely encounter even more applications of these versatile mathematical concepts.